Welcome, everyone. I'm excited to kick off our presentation today. We'll be exploring the fascinating concepts of surface area and volume. The title of our talk is PowerPoint Presentation on Surface Area and Volume. Throughout this session, we'll cover the basics of these important math topics, see some real-world examples, and learn how to calculate them. Let's get started. Let's take a closer look at the contents of this presentation. On this slide, we see a list of various geometric shapes and their associated properties. The main focus here is on understanding the different formulas and concepts related to each shape, such as surface area and volume. For example, you'll notice entries like the volume of sphere and the surface area of cone, which are fundamental in calculating the space these shapes occupy and their outer surface. Similarly, shapes like cubes, cuboids, cylinders, hemispheres, and frustums are all covered, each with their specific formulas. It's important to remember that these concepts are interconnected. Knowing how to find the surface area helps in understanding the total exterior part of a shape, while volume tells us about the space inside. Both are crucial in real-world applications, from engineering to architecture. Throughout this presentation, we'll explore each of these shapes in detail, highlighting the key formulas and their practical significance. This comprehensive overview will help you grasp the fundamentals and apply them confidently in various scenarios. All right, let's take a closer look at the different shapes we'll be exploring today. Starting with the hemisphere, which is essentially half of a sphere, kind of like a dome. It's a three-dimensional shape with a curved surface. Next, we have the cone, which tapers smoothly from a flat base to a point, kind of like an ice cream cone. Moving on, the number 6 here refers to the cuboid, a box-shaped figure with 6 rectangular faces. Think of a brick or a shoebox. The number 4 points to the sphere, which is perfectly round and smooth, like a ball. The number 2 highlights the frustum, which is basically a truncated cone or pyramid. Imagine a cone with the top cut off. Then, we see the sphere again at number 7, emphasizing its importance. Number 5 indicates the cylinder, which has 2 parallel circular bases connected by a curved surface, similar to a can or a pipe. Lastly, number 3 is the cube, a special type of cuboid where all sides are equal, like a dice. These shapes are fundamental in understanding geometry and help us visualize objects in both real life and abstract concepts. Throughout this presentation, we'll see how these shapes play a key role in various applications and why understanding their properties matters. All right, let's dive into the surface area of a cube. On this slide, you'll see 2 key formulas. The first one, 4 times the side squared, represents the lateral surface area. This means we're only looking at the sides that surround the cube, excluding the top and bottom. The second formula, 6 times the side squared, gives us the total surface area of the cube, which includes all 6 faces. What's important to note here is that both formulas are based on the side length, which is the edge of the cube. By understanding these formulas, we can easily calculate how much surface the cube has, whether we're interested in just the sides or the entire outer surface. This is a fundamental concept because it helps us relate the size of an object to the area it covers. As we move forward, keep in mind how these formulas can be applied to real-world problems involving surface area calculations. Let's take a closer look at the volume of a cube. As you can see, it's expressed as side cubed, or side to the power of 3. This means that if you know the length of one side, you can find the total volume by raising that measurement to the 3rd power. For example, if each side of the cube measures 2.2 units, then we simply cube that number to determine its volume. This concept is fundamental because it shows how volume scales with the size of the cube. Understanding this helps us grasp how changing the dimensions affects the overall space inside the cube, which ties into our broader discussion of geometric measurements and spatial reasoning. Now let's take a closer look at the cuboid. The cuboid is a 3-dimensional shape, and you might also hear it called a rectangular prism. What makes it interesting is that it has 6 faces, all of which are rectangles. These faces come together at right angles, giving it that classic box-like shape. One of the key points to remember is that the cuboid has 3 pairs of opposite faces that are equal in size. For example, the top and bottom faces are the same, as well as the front and back, and the left and right sides. This symmetry is important when calculating surface area or volume. Speaking of volume, since each face is a rectangle, the volume of a cuboid can be calculated by multiplying its length, width, and height. Similarly, the surface area involves summing up the areas of all 6 faces, which is quite straightforward once you understand the dimensions. Connecting this to our overall theme, understanding the cuboid helps us grasp how 3-dimensional shapes are structured and how their properties are related. It's fundamental in fields like engineering, architecture, and design, anywhere we need to model real-world objects accurately. Now, let's look at how we determine the surface areas of a cuboid. The lateral surface area, which is the area of all the sides excluding the top and bottom, can be calculated using the formula 2 times the sum of the length times the height plus the breadth times the height. Essentially, we're adding up the areas of the vertical sides. Moving on to the total surface area, which includes every face of the cuboid, the formula is a bit more comprehensive. 2 times the sum of the products of length and breadth, breadth and height, and length and height. This accounts for all 6 faces of the cuboid, providing a complete picture of its surface coverage. Understanding these formulas is key because they help us quickly find the surface areas, which is essential in many practical applications, from packaging to construction. They also connect to the overall theme of understanding 3-dimensional shapes and their properties, which is fundamental in geometry. Let's take a closer look at the volume of a cuboid. As you can see, it's calculated by multiplying the length, L, by the breadth, B, and the height, H. This formula is fundamental because it helps us understand how much space a cuboid occupies. When we talk about the volume, we're essentially measuring the capacity inside the shape. It's important to grasp this because many real-world objects are cuboids, like boxes or rooms. Remember, the volume is directly proportional to each of these dimensions. If one increases, the volume increases accordingly. This concept ties into the overall theme of understanding 3-dimensional shapes and their properties. So, whenever you're working with a cuboid, just think about multiplying these 3 measurements to find out how much space it contains. Now, let's take a closer look at the cylinder. The cylinder is a fundamental shape in geometry, characterized by its circular bases that are parallel and equal in size. One of the key points to remember is that the height of the cylinder is the distance between these 2 bases. It's interesting because cylinders are everywhere around us, from the cans we use daily to the pipes that carry water. When we analyze a cylinder, we focus on its surface area and volume. The surface area combines the area of the 2 circular bases plus the side, which is curved. The volume, on the other hand, tells us how much space is inside the cylinder, great for understanding capacity. Connecting this to our overall theme, cylinders help us understand how 3-dimensional objects work, especially in real-world applications like engineering, manufacturing, and design. They're simple yet incredibly useful shapes that demonstrate core principles of geometry in action. Dehaveakratkoite yerabeerate emven eman yenafoderamu el yero. Esveya zayan yeru ya espaveya erkawanomesta yeri yutse, elen de era. Zedeya es yeri, unas ya esta yeri f, o erem uelea de elya pedoln o kratkoi pedoveya erkawanomesta itse, elen de era. Kavote o eraya veyeruga elya de tete akea. Pedarich pe elu, estevea erazea pe erkavea de erate, o veera velen o devem pedi umn. Oje te yeri anasu uth, iarete, okea eluche yevea fa eram uelea. Pelte olemuchete o anapel emogayete, ena emope erya de yelite yeri obestia, uyupe elostea de yeri, petoveyer kelanonestetse, elin de erea. Uche te yeru vea ya kelakea beokeove uyu. Te akeli deveya keru geoveyeru ya o esanove. Te yepeya yeri. Yes, lem yergavo ariamo beokelavo kratkoi pelveyer kelanoesteti. Te oyeyo pelostea de yeri, operia de yelia yete esya kelakea tu periericha telvea jana yachaeste yeri. Pelotel amuchete o emye, and en o en apelokela ze yeruve ayeta. Eskalodel yeri, kalonamate ye iria el pelote, iria be uyete. Esye de el ye pelokea yerute ye belokea veo kratkoi, chelawes telitse, elen de era. Terakea je ye yeruvidi dedi Chatao te eleforum uelelias te yerios anovea de elia peloenium a en ialabeste kratkoi, pelovea erkelanoes telitse, elen de era. Chateloas obeya en ovea jano de elia zea de eche. Esvea ze en, yerukoeseroes che yete, a te ye iria elove eliobe yer ye emove. Etedia forum el yerpelamo gayute en amalucha shayapel en yate yerias te erukete urutse, elien de era iegos veo kratkoi esteve. Chataya velia yetes yavea jano kratkoi, chatawas te yeri uena shaya kratkoi, obeshaya kratkoi te ye yerogeyo yete, eriche ye eskelikea te ye alakea. Teya peya yeri, dehavea kratkoi teya pelgaveo eris amotel Kalakilero ssj te yervea te yeri, obeyer yam se elien de era. Enalatel msla kratkoi de yeveyeru vidi didi te ye f oderamuelu. Kalatel era ye pelmoga yete ope ye de yeli te yeri, obeyer yem. Zede ye es yeri vejano pelanya te yeri. Chate obeyer yem se elien de era zeaviasita te devuko esanove en yerukope era yete erove. Era deus aosanove en yeli veyeru esote yero. Eforemu ela veyeruga elya de tetakea. Higher to age. Ete ozana chete. Chete o yerube ye ya era deus. Veoze veo de ye gerovika vea de erate. UMN oje a yelemena che esla paisea te ye umn oje a yelemena veyeru esoteu. Ete ote era es che yete peokela ze yeruve ayete. Escalal el yeri calapelero este era en este ve auzeal en ayetetse, elen de erve en ute eri. Peloen en iezateo krakui, afoderemu el yeroche yelen yeri vejano. Pelotela muchete o en apelamo gayete en alameria shiate yeri yel yeri en yeru yezadacheti. En aperium yeder. Veyeruche yesalyate yeri obe yer ye yeze yeder veuer ove yelikeo en te kratkoi, en ye erove. Pelodete o demu. Zea pero iteya. Chete odi ye en oete efoder ula el yeje ite veolesen ove yerope ye de ye el ye en yerobe yer yelametse elen de era. Today, I want to focus on the concept of a cone. A cone is a three-dimensional geometric shape that tapers smoothly from a flat, round base to a single point called the apex. It's a shape we see in everyday life, like an ice cream cone or a traffic cone. The key points to remember are the shape's curved surface and its circular base. The cone's defining features are its height, radius, and slant height, which all play a role in calculating its surface area and volume. Understanding cones is important because they help us grasp how different shapes are structured and how their properties relate to real-world objects. This ties into our overall theme of understanding geometric forms and their applications. So, when you think of a cone, picture that smooth transition from wide to pointed, and remember how this shape appears in many practical situations around us. Now let's take a look at the surface areas of a cone. The lateral surface area of a cone is given by the formula 2 pi times L, plus some extra. Here, L represents the slant height, and R is the radius of the base. Think of the lateral surface as the side part of the cone that wraps around, excluding the base. Moving on, the total surface area of the cone combines the lateral surface area with the area of the base. This is expressed as pi times L plus R. Essentially, we add the slant height component to the radius to account for the entire surface that covers the cone. Understanding these formulas is key because they help us find the surface area, which is important in real-world applications like packaging or manufacturing where material quantity matters. So, in summary, the lateral surface area focuses on just the sides, and the total surface area includes the base as well. Both formulas are crucial tools in calculating the amount of material needed to cover a cone-shaped object. Let's take a closer look at the formula for the volume of a cone, which is 1/3 pi R2H. This might seem a bit complex at first, but once you understand each component, it becomes much clearer. The PR2 part represents the area of the base of the cone, since the base is a circle. The H stands for the height of the cone, which is the perpendicular distance from the base to the tip. And the 1-3 factor is crucial. It tells us that a cone's volume is 1/3 of the volume of a cylinder with the same base and height. So, in essence, this formula combines the base area with the height, scaled down by 1/3, to give us the cone's total volume. Understanding this relationship helps us see how the shape of the cone influences its capacity, which ties back into our broader discussion on how geometric formulas describe real-world objects. Now, let's take a closer look at the surface area of a sphere. The formula we're focusing on here is 4πr2. This formula is quite elegant and simple, but it's also very powerful. It tells us that the surface area depends directly on the radius of the sphere. As the radius increases, the surface area grows proportionally to the square of the radius. So, if you double the radius, the surface area actually becomes 4 times larger. This is a key point because it highlights how sensitive the surface area is to changes in size. Understanding this relationship is crucial when we're working with spherical objects in real-world applications, from designing tanks to understanding planetary surfaces. Remember, the 4πr2 formula captures the essence of a sphere's surface, making it a fundamental concept in geometry. Now, let's take a closer look at the volume of a sphere, which is represented by the formula 4.3πr3. This formula tells us that the volume depends on the radius of the sphere, raised to the 3rd power. The key takeaway here is that, as the radius increases, the volume grows quite rapidly, since we're cubbing the radius. This is an important concept because it highlights how small changes in the radius can lead to significant differences in volume. When we compare this to other shapes, the sphere's volume formula is elegant and symmetrical, reflecting its perfect roundness. Understanding this formula helps us grasp the relationship between the size of a sphere and how much space it occupies, tying into the broader theme of geometric measurements and their real-world applications. Let's now turn our focus to the hemisphere. When we talk about hemispheres in this context, we're referring to the division of the brain into 2 halves, the left and the right. Each hemisphere has its unique functions and specializations. For example, the left hemisphere is often associated with logical thinking, language, and analytical skills. Meanwhile, the right hemisphere tends to be more involved with creativity, spatial awareness, and holistic processing. Understanding this division helps us appreciate how complex and specialized our brain's functions truly are. It also highlights the importance of considering both hemispheres when exploring cognitive processes, especially in fields like neuroscience and psychology. Overall, recognizing the roles of each hemisphere allows us to better understand human behavior and mental functioning in a more comprehensive way. Now, let's take a closer look at the surface areas of a hemisphere. The curved surface area, which is the area of the curved part of the hemisphere, is given by 2 times pi times the radius squared. This formula highlights how the curved surface depends on the radius. The larger the radius, the greater the curved surface area. Next, we have the total surface area of the hemisphere, which includes both the curved surface and the base. This total area is expressed as 3 times pi times the radius squared. Essentially, it's the curved surface area plus the area of the flat circular base, which is pi times r squared. Understanding these formulas is important because they help us calculate how much material or paint is needed to cover a hemisphere or how to determine surface properties in real-world applications. Finally, note that the surface area of the hemisphere is 7.1 times pi times the radius squared, which is a way to express the total surface area in a simplified numerical form. Recognizing these relationships allows us to better grasp the geometric properties of hemispheres and their practical uses. Te yepe ye yeri. Deravea kratkuite, yepero geravea eri m, on abe yer ye m yepero lusf ye yero. Inazate olem sla kratkui de ye m yerovedi dedium f eremu elutu 3 per 3. Cheteo zanache yete. Cheteo be yer ye m pero lusf ye yeru erave ye endevu m te yete yeri. E ema be yer ye ema pero ln o kratkui, sf ye yero. Veja en apelenya te yeri. Chateo be yer yelam sf ya yero ero ssj te yero vaya te s ya pel efoder muel ya 4-3 peter 3. Ayapel elu sf ya eraya. Kala kapel elovidiana sf ya yero. Zaya eniama yeta de veyeta yeta oga o be yer yelama. Ina ata o msla kratkoi de yete. Akea jeyu kea zaya en o. Chete ola be yer ya mpel lusf ya yero era ve ya en 7.2. Atal ke o en ke yeta en o ya che yesalove o yeza. Ina che ya en iya. Kaloteo era ya pedalamo get yetelena empedal in ya te yeri emma asheate abidi era za ya yeru be yer ya keatelve. Es kaloteo yeru yeru era baute a yadam. Ate ya emma che ya en yeri vajana. Peloteo muchateo en apel kilaza yerve yeta. Kalakeamo jano be yerwestero of a yeru che yesalite yeri be yer ya empedal sf yeter yeru. Ieskal de yelize veyesta eno kratkoi. Eforemu yeru de ya pel eleno kratkoi sf ye yeru. Pel en an iya atidike eforemu kavaze aliamo esvayaze ipelolemo gayete. Enanamalucha sha yela yelente. Idero veate yeri. Esya vege ya o yete. Iriche ya eskelike zea dea cha keli o de ya eli ero valenidi. Vetse ya elothem. Zelena eni ya beyer ya emapel elu sf yeter yeru. Atadi eni zakel yuche ya veyer kelel yelem yelente. Of Adel yeler yashaya eni ya bel ya esalojan yer kaza dacha velbela estata ya kelem ya ano krakoi ge ya yete. Enja ya ya Let's talk about the frustum. The frustum is essentially a truncated cone or pyramid, which means it's a shape formed by slicing off the top of a cone or pyramid with a flat, parallel cut. This shape is really useful in many applications, especially in computer graphics and 3D modeling, because it represents the visible area of a scene. Think of it as the view volume of a camera. The key points to remember are that the frustum has two parallel bases, one smaller, one larger, and the sides are usually tapered. Understanding the frustum helps us grasp how cameras capture scenes and how projections are managed in 3D space. So, in the context of our overall theme, the frustum is a vital concept because it defines the boundaries of what we see and how we visualize 3D objects on a 2D screen. Ta yepaya yeri de havea krakkoite, yepel esamote iemina aforem yeru de elya veyeru chayes elya en, iepel veya kilanoeste, us yachaya en ogokeo en usa. Enatel mesele kratkoi de ya veyeru de ya lel de veyeve aja en yeru yacha este. Peyeter ve'eya. Etal kaleri vel elienya kratkoi, en aya pelveyer kalanoes tayeri. Ili bel kalveya pelveya, kalanoes tayeri us yachaya, en enogel kalen usa. Yeya pe elosh jaya de yeri veyeru chayes el yayeta, es ye pel efa ul yepa, r plus rl. Zedeya es yeri pe. Etal chayes elopei. RER era de us yeru emya en yeri shaya geo bel el yeri shaya geo asanova enia kratkoi. El enake elo enaya ve yeru esotea. Elio be era zeu yushea aya. Ete efoder ele pelkila zeyer ve yete. Chateo belkila ve ya pel ve ye erkea enos te yeri zea vidiasita ote. Yeru era de us ove de len yeru enake elo en o kratkoi lene. De el yeya. Pero el enaya pel ve ye erkea enos te yeri us yacha ye en enogeo keo enusa. De el yo etel ge okebe okeo veo kratkoi pelve ye kelano este, idealbe eve el ye ute pe eloshea de devu kelo esanove alenia kratkoi. Fa ele veyurga el ya de tete akea. Tu pe r plus r l pe us pe r2 e pe r2. Pe yeler veya cheo este yeri. Eteo deveo ye en enaya be okeo veya pelve ye kelano este yeri. Aveteo ya. Pe eloshea de yo esanove alenia kratkoi. Obeira tete yeva enia malania. Chatel pel enia ma enia tedikela foremu el veaja eno. Pelotel muchatel eni poemo get ayutan alem teochelen o ero ss te yerovea te yeri, pel eloshea de yeri, pel veyer kelen este te akeo kratkoi efige yero. Vetse ye el odem. Etedi efoderem ul yer pel zeveo el yute el yage kelo en akeo dedite yeri kelakea be okeo ve uyu. Te akeli pel en uyu pe eloshea de yeri pel veye kelen te us yacha ye en ogel kelo en usa. Chata alacha ya en yeri vijajan. Alvedi en ja ya en ya en. Yerukao ya erkao ita yakata u en yerukao zaya da chaka. Ta yapaya yeri de havea kratkoita. Yapaya ya kratkoi de ya mkapal sl ya de en yazamu sla kratkoi deo. Gede ya SSMota EMF oderamu elu abayer ya maus ya cha ya en agao kao nusa. ELEF erushata UMA. Ina ake era ya vayervade ta ya F oramu elu. 1 3 pi h R2 plus R2 plus RR. Eta F oramu elu cha ya en yeri vajana. Pelatawa muchatao an abayer ya de en ya yetera de us yeras an avani yeli vayer kilan ya kratkoi cha este. Ata ke ya vayeru esota uf ige yero. Oberate te yeva eniam ania. Chatels a deas yeri perisutas tevoyeta, esumem akaveadera talve era deus ove perois ove yediani era deus ove. Chatalpel dechayer kilivayeta veli yalani yalboi kao esan ove alani akratkoi, and albeshje akratkoi obe yer yalem. Kalogede yerugalvel ariama eferushete uamake. Vejanopelem enita yeri. Chatawate eleforamuela pelamogizayetana akratkoi te tacha en yerukratkoi, obeyer ya mlu akratkoi, us yacha ya en akratkoi kal enu, esal be erazano akratkoi, efige yero. Kalatela era yave esta yacha ayeta. Es yave eraza elicha en yerukea enja ya enya, en yerukea erkea itaya keata en yerukea za ada achaka. Eteladan a Ezekiel Uchaya Vayorka Eforamuel. Kalata era yo esveya zayurvayetava esyepa area de yordoshe, yekoensa yepetsa. Ya bayer ya akilipamagayeta en eryasheata yeri area el yeri en yeruyeza adache. En adeya us yeri. Chatalteya payer yeri uvea esyavesta yeri chayate kawayapa en iya. Kalaka pe eridem yelanyata yeri, ta ufrmulu, ena pe erakatadi kayali vecha ya ya asanove, ena yatsa yan en oesta yeri.